do this question. Okay, sodium carbonate is a compound with a wide variety of uses, such as regulating pH in swimming pool. Okay, so carbonate can actually take in a H plus once to form HCO3 minus, can take a H plus another time to form CO2 plus water. So calculate the pH of sodium carbonate, ignore the effect of pKb2. So actually what you're doing is you're actually only using carbonate plus water to give you HCO3 minus plus OH minus. So carbonate is a base. So since it's a weak base, we're going to apply using this formula. OH minus is equals to, concentrate OH minus equals to square root Kb. Okay, in this case, it's Kb1. Okay, they say ignore Kb2. So Kb1 times the concentration of carbonate. Alright. So this would be equals to square root. Okay, if you plug in the values, Kb1 is 10 to the power minus 6.3 times the concentration of carbonate, which is 0.1. You get OH minus concentration to be 2.23 times 10 to the power minus 4. Okay, and of course with that you can find out POH. POH equals to minus log OH minus, okay, which is actually minus log 2.23 times 10 to the power minus 4. That gives you a POH of 3.65. Alright, so what's pH? pH is 14 minus POH. Plug it in yourself and you should get 10.35. Alright, so that's answer for part A. Okay, the next part, 20 cm cube of sodium carbonate was titrated against 50 cm cube of hydrochloric acid. Calculate the final pH of the solution. Okay, so how do we do a question like that? Okay, let's take a look. So I want you to imagine, all right, the sodium carbonate, right, carbonate will react with H plus. Can you see that? And then it will form HCO3 minus. All right. Okay, so you must be able to see that. You must be able to see that the volume of H plus that's needed for the first equivalence point is this. So carbonate, I'm going to write down 20 cm cube times, and the concentration is 0.1 mole per dm cube, right? So to reach the first equivalence point, since this one has the same concentration, all right, same concentration as the carbonate, to reach the first equivalence point, I also need 20 cm cube. Are you me? So the graph should look something along this line. So I'm going to give you an idea. Okay, I'm going to put it out here, right? Okay, so this is what the graph should look like. So I'm going to jump ahead and talk about 3. So the carbonate, you started over here, carbonate. Okay, you started carbonate right over here. You're gonna reach the first equivalence point. When you reach the first equivalence point, this is HCO3 minus, and after that over here you get CO2 plus water. Alright, so I just showed you that you need 20 cm cube of H plus to form HCO3 minus. So this is 20. Alright, so the HCO3 minus will need another amount of H plus, right? So this amount of H plus needed again, this HCO3 minus is this one over here. So this HCO3 minus will need another bulk of 20 cm cube to become CO2 plus H2O. Right? So over here it will be 40. Okay, but you can see that the question said you add up all the way to 50, right? So this is actually 50. So you realize that this at this point is actually kind of acidic, all right? It's kind of acidic. It's because of the HCl, all right? Because of HCl. So by the time you reach this point, all right, all the carbonate and hydrocarbonate all have reacted. This is the end of the reaction. So whatever HCl you put in from here onwards remain as HCl. Okay, so you realize that the excess HCl from here onwards is actually 10 cm cube. You see that? 10 cm cube. So we're going to calculate the number moles of H plus at this point. Okay, it's actually 10 over 1000 times 0.1. Can you see that? So that will be 0.001 mole. So the concentration of H plus present at that point is 0.001 divided by the volume. Okay, what's the volume? So the carbonate at first was 20 cm cube. Remember? It was 20. You started 20 cm cube, right? So the carbonate over here was 20 cm cube. So you added 50 cm cube of the acid. So the total volume at that point, right? Can you imagine the total volume at that point is actually 70 cm cube. So the H plus ions are floating in this volume of 70 cm cube. So you divide by 70 over 1,000. Alright, and that will give you a value of 0.0142286 moles per dm cube. Alright, okay, so then you can find out the H plus. Alright, H plus equals to minus log H plus concentration. Just plug it in and you get answer of 1.845. Okay, so this value here should be 1.85 to 3SF, right? Here is 1.85. Okay, so this is 1.85. Got it? Okay, so yeah, so this is how we do it. So this is for part B. Okay, for part C, since I already mostly sketched the curve, right? So a few things you need to take note of. They say they want you to clearly label any significant pH values and volume. Okay, so what is required over here? You definitely need to find out the pH of the maximum buffer. Okay, so this initial you already know, right? It's 10.35. Just now we calculated. You see that? Okay, so we need to know the pH of the maximum buffer, which is actually over here and over here. So you need to label the volume 10 and 30. Okay, how to find out the maximum buffer? Okay, so because over here, right, you have carbonate and hydrocarbonate, so that's a buffer. And over here you have hydrocarbonate and you can take it as H2CO3, right? So that's also another buffer. So max buffer, these are called max buffer. So max buffer formula is pH equals to pKa or pOH equals to pKb. Okay, in this case, if you look at the question, we do have pKb, all right? So so it means that for the first equivalence, first maximum buffer, pOH equals to pKb, right? pKb1, that will be 6.3. So you try to find out the pH, it will be 14 minus 6.3, and that will give you a value of 7.7. So that is the max buffer at this point, 7.7. So in order to calculate the max buffer for the other point, we use the other pKb. So pOH equals to pKb2, which is actually, let me check it out again, 10.3. So pH equals to 14 minus pOH. So this will give you a value of 3.7. So this is where you label 3.7. Okay, so this is how we do the question. Okay, so let's look at the next part. Two indicators are needed. We are doing a part D now. Two indicators are needed for this titration. The table below shows the working ranges and colors of some common indicators. Okay, so what are the indicators is needed to find out the first equivalence and second equivalence? Okay, the first equivalence is here, and the second equivalence is over here. So the first equivalence, let's take a look. Okay, the first equivalence, you notice the change, right? It's somewhere between 3.7 to 7.7. So we're going to take a look, 3.7 to 7.7. I think the best answer is this. All right. So it started from a base, and then it will change. It becomes more acidic, right? As you add the acid, it becomes more acidic. So the color should be blue to yellow, but you don't write blue to yellow. So the first answer for the first equivalence, you need actually bromo more blue. Okay, what is the color change? You must write blue to, okay, this is a bit tricky. You can't write blue to yellow. Okay, where it changes, the end point where it starts to change color is actually somewhere in between yellow and blue, which is actually green. Okay, so you must put blue to green. So if you don't know why is it green, maybe you can think of the rainbow color ROYGBIB, right? So yellow and blue will give you green. Okay, so you actually get to green. Okay, the second equivalence point. Okay, I guess this is the pH range. It's around here. Maybe I think it's between like 2 to 4. Between 2 to 4, right? So I think a good indicator you can use definitely would be methyl yellow. Okay, methyl yellow. And again, the color change will be yellow to, you don't say yellow to red, between orange, between yellow and red is orange, right? So you must write the color change is from yellow to orange. Okay, so this is exactly how you do the first part. Okay, let's see how we do question 2. Right, so they say there's a sample of water. Okay, there's a sample of water containing these two at pH 3, right over here. So in what they're trying to say is initially is already a buffer. Okay, initially is already a buffer because it consists of both of these. Okay, and was titrated with sodium hydroxide using 2 indicators. Okay, the titration is as shown. Okay, write down the 2 equations that occur at each equivalence point when sodium hydroxide is added into the sample of water. So to reach the first equivalence, right? Okay, so you must understand there are a few things here. All right, so maybe I should draw it out nicely. So initially there's H2CO3 and HCO3 minus. All right. So I put this on original. So the first part is H2CO3 will react with the base to reach the first equivalence point. The H2CO3 will react with NaOH to give you NaHCO3 plus water. Alright, so that's the first reaction, okay, to reach here. So at this point, there are actually HCO3 minus from, I'm going to write down now, from H2CO3, and I also have HCO3 minus initially. The origin, which is the original, okay, because it didn't change, it didn't react at all as you move from here to here. Okay, so this initial and original are the same thing. So to the second equivalence point, okay, to the second equivalence point, the NaHCO3 will continue to react with NaOH, and you form Na2CO3 plus water. Alright, but this NaHCO3 came from 2 places. Got it? Okay, so let's take a look. We can find out from here, since you needed only 10 cm cube, so the number moles of OH minus, right, to neutralize sodium H2CO3 will be equals to volume times concentration. Okay, I think they gave you the concentration, right, 0.1. So the number moles of OH minus actually initially is 0.001. Okay, and this actually is the same as the number moles of H2CO3. So the concentration of H2CO3 initially, right, is equals to 0.001. You divide by the volume. Okay, the volume is actually 10 cm cube divided by 10 over 1000. Okay, so this will give you a value of 0.1 mole per dm cube. Okay, so we found out the first part. Okay, so take note for the second part, the NaHCO3, right? There are 2 portions. Okay, so one portion came from one portion of the HCO3 minus came from sodium hydrogen carbonate, and the other one is the original. Okay, so I'll say I'm going to write it out both. Maybe I write it out 2 times so that maybe it'll make it clearer. So this is the initial. Put this initial, and this one is actually from H2CO3. Okay, so from H2CO3, right, NaHCO3, it requires another 0.00. Sorry, it requires another maybe I write that again first. Easier. So this one from from the NaHCO3 from H2CO3, right, requires another 0.001 mole of NaOH. Can you see that? Okay, and the initial one will require how much? Okay, so how much of it will be needed over here? Actually, you can tell because you can see that from here, if I calculate, right, this area, right, the number of moles of OH minus to reach second equivalence point, right, you realize it's actually equals to 30 over 1000 times 0.1, which is 0.003. So, but 0.001 was used to neutralize the NaHCO3 from the initial part. So, which means from the H2CO3, so the initial, okay, the initial, which is this one, will require, of course, how much does it require? Of course, it will require only 0.002. Okay, means out of the 0.003, 0.001 was used to neutralize the NaHCO3 that came from H2CO3. Okay, and 0.002 moles must be used to neutralize the NaHCO3 that was from the initial. Okay, the initial, which is this one here. Can you see that? Which means the amount of NaHCO3 will also be 0.002. So we can calculate the concentration of NaHCO3, otherwise I just write it as HCO3 minus, to be 0.002 divided by the volume, okay, the initial volume. So this gives you a concentration of 0.2 moles per dm cube. Okay, so that's how we do it, right? So that's the first part. Okay, then they say using information given and answers in A part 1, calculate the acid dissociation constant of the above reaction. So we're going to use this point because this value is given 3.9 and this is a buffer, right? So this is a buffer. So because it's a buffer, we apply buffer formula. pH equals to pKa plus log concentration of the conjugate base over the acid. So I'm going to just plug it in. 3.9 equals to pKa plus log. Okay, what's the concentration? This is 0.2, right? And this is 0.1. Okay, so which means you can actually calculate the pKa, which turns out to be 3.599. So the Ka is 10 to the power minus 3.599, and that gives you a value of 2.52 times 10 to the power minus 4 moles per dm cube. Alright, so that's how we do part 2. Okay, last part. Using your answer in A part 2 means this is the buffer. Calculate the new pH when so much sodium hydroxide is added. Okay, so the first thing you need to do is write the equation. So OH minus being a base, it will react with H2CO3. And you form HCO3 minus plus water. Okay, so that's what happens when you add OH minus into the buffer. Right, so I'm going to put initial, change, final. Alright, all in terms of moles per dm cube. Okay, because there's no change in volume, this is a solid. Can you see that? So I'm just going to calculate the number of moles of sodium hydroxide. Or maybe I should do, I can do it straight away. I want to find out the concentration of OH minus when I add it in. So I can find out number of moles, which is 0.8 divided by the MR, right? Can divide MR. But it's very nice. This is 1 dm cube. So divide by 1 dm cube, like so moles per dm cube. So this works out to be 0.02 moles per dm cube. Okay, so initially H2CO3 is, let me see, H2CO3 is 0.1. Can HCO3 minus is 0.2. The OH minus that you added in is 0.02. So they will react. Okay, they will react. This being limiting. So minus 0.02 minus 0.02 plus 0.02. So this becomes 0.080 and 0.22. Alright, so this at the end, this is still a buffer because you have HCO3 minus and H2CO3. So since it's a buffer, you still apply buffer formula. pH equals to pKa plus log conjugate base over acid. So if you plug it all, put in all the numbers, pKa, right? Just not pKa, I think we can use this part here. 3.599 plus log 0.22 divided by 0.08. Okay, press your calculator. So you can imagine when you added a base, right? You expect the pH to go up slightly. So from 3.9, just now was from 3.9, right? Yeah, we saw original was 3.9, so the pH must have gone up slightly. So now if you calculate, it's actually 4.04. Right, so this is exactly how we do the question.